Today, we're going to break down the exact lab procedure for measuring boron in soil. We're taking a complex chemical analysis and turning it into a series of clear, simple steps.
So let's start with the big question. Why is this test so important? Well, you can think of boron as a Goldilocks nutrient for plants. The amount has to be just right. Too little or too much can be a total disaster for crop health. You see, boron is a micronutrient. Plants only need it in tiny, tiny amounts. But that amount is absolutely critical. And the line between what's helpful and what's toxic is razor thin. That's why being able to measure it precisely is so essential for any grower. And the stakes are really high. If you have too little boron, you get stunted growth and terrible pollination. But if you have too much, you've basically poisoned the plant. Its leaves turn yellow and it can die. This is exactly why we need a reliable, repeatable test. Okay, let's get into the lab work. The first part of the process is all about prep and extraction. Our goal here is to pull the boron that plants can actually use out of the soil and into a liquid that we can test. And the best way to do that is with hot water, because it's great at dissolving the specific forms of boron that plants absorb. Now, this extraction process might look like a simple 4-step recipe, but don't let that fool you. Every single step requires absolute precision. The amounts, the timing, it all has to be perfect if you want an accurate result. Let's break it down. We kick things off with an air-dried soil sample, and we weigh out exactly 25 grams. In a lab, consistency is everything, and this is where it all starts. Next, we add 50 milliliters of double distilled water. We use the super pure stuff to make sure there's no contamination. We also toss in a little activated charcoal. Its job is to absorb any organic gunk, which guarantees that our final liquid extract is perfectly clear for the next stage. Then, the whole mixture gets boiled for precisely 5 minutes. This is that hot water extraction in action. The heat forces the water-soluble boron to let go of the soil particles and dissolve right into the solution. And now for the really cool part, a little bit of chemistry magic. You see, the boron in our filtered liquid is completely invisible. So to measure it, we have to use a chemical reaction to make it show itself by giving it a color. The key ingredient here is a chemical called azomethane H. This stuff is designed specifically to seek out and bind with boron. And when it does, it creates a yellow compound. Here's the brilliant part. The intensity of that yellow color is directly proportional to the amount of boron in the sample. To make sure this reaction works perfectly, we follow another very precise procedure. We take 5 milliliters of our clear soil extract, add a buffer solution to keep the chemistry stable, and then add the azomethane H. After that, we just wait for 30 minutes. This gives the reaction time to finish and for that yellow color to fully develop. Once the color is ready, we can't just guess how yellow it is. We need a special instrument called a spectrophotometer. It works by shining a beam of light at a very specific wavelength, 420 nanometers, through the sample and measuring exactly how much of that light gets absorbed. This gives us a precise number for the color's intensity. But wait, how does a number for color intensity tell us how much boron there is? I mean, a number from a machine doesn't mean anything by itself. For that, we need to create a special kind of scientific ruler to translate that color reading into an actual boron concentration. The best way to think about it is like a paint color chart from the hardware store. You hold a paint chip up to the wall to identify the color, right? We're basically doing the same thing here, comparing our soil sample's color to a set of standards we've already prepared. In science, we call this ruler a standard curve, or a calibration curve. And honestly, it's a fundamental tool in analytical chemistry that makes this entire test possible. To build this curve, we first prepare a series of standard solutions. These are samples that contain exact known amounts of boron. We then treat them with azomethane H, developing their color in the exact same way we did with our soil sample. And here's where it all comes together. We measure the color intensity of each of those standard solutions and then plot the values on a graph. With the known concentration on one axis and the color reading on the other, the points form a perfect straight line. This is our calibration curve. This is our ruler. And this makes the final measurement incredibly simple. You take the color reading from our unknown soil sample, find that value on the graph, trace it over to the line, and then drop straight down to the other axis. The value you land on, that's the boron concentration. Okay, we are almost there. We have the boron concentration from the curve, but that's for our liquid sample. To get the final answer for the soil itself, we just need to do one last calculation to get it into useful units.
After all that chemistry, the final math is actually pretty simple. You take the concentration from the curve, let's call it C, and you just multiply it by a dilution factor of 10. This converts the result into milligrams per kilogram, which is the standard way to report soil nutrients.
Now, that factor of 10 isn't just a random number. It's there to correct for the dilutions we made earlier. Remember starting with 25 grams of soil and 50 milliliters of water? That's a 2x dilution. Then, we only used 5 milliliters of that extract for the color reaction. That's another 5x dilution. So 2 times 5 gives us our total dilution factor of 10. So let's walk through a quick example. If our calibration curve told us the concentration C was 0.06 micrograms per milliliter, we multiply that by 10. Our final result for the soil is 0.6 milligrams per kilogram, a clear, actionable number that a farmer can actually use to make decisions.